So let's get started with today's class. So today we are essentially going to look at an example of how to design a lead compensator. Okay, that's going to be our exercise for today. So let's do the design from the start, right? So that's what we are going to do. Okay. So let me write down the problem statement, then we will get started with the design process. Okay. So the example that we are going to consider is that we consider a system or a plant whose transfer function is the following. Okay. So we consider a system or a plant whose transfer function is P of S, that's given as 4 divided by S times S plus 2. Okay. So that is the plant transfer function. Okay. So what we need to do is that we need to design a lead compensator such that the static velocity error constant KVE, if you remember what was KVE, that's the static velocity error constant, right? So that's 20. The phase margin gamma, that should be at least 50 degrees. Okay. And the gain margin is at least 10 decibels. Okay. So, and of course consider unity negative feedback. Okay. So that's what we want to do. So we can have unity negative feedback. Okay. So that's the problem statement, right? So as far as the design of this particular lead compensator is concerned, so we have a plant to begin with, which is whose transfer function is 4 divided by S times S plus 2, right? So do you think the plant is stable or unstable or marginally stable? Of course, yeah. So it depends on how you look at it, right? So yeah, so you immediately observe that there are the plant poles are at -2 and 0, right? It has a pole at the origin. So you give a step input, anyway the output is going to become unbounded, right? So so you can call it either marginally stable or unstable also, right? Because the definition of Bibo stability means that the output should be bounded for all possible bounded inputs, right? So essentially we want to stabilize the closed loop system, right? So that is also a main objective. At the same time, we also want to ensure that some performance specifications are met, right? When we design controllers or compensators using frequency domain techniques, as we discussed yesterday, the performance parameters are going to be specified in terms of gain margin, phase margin, steady state error characteristics and so on, right? Here KVE essentially is a static velocity error constant, if you remember. Right, we will define that once again, and so that essentially tells us, what will be the magnitude of the steady state errors, when we give a step input or a ramp input and so on, right? So that's something which we would use for our design process. Okay. So now, in order to get started, please remember that this is our basic feedback diagram. Okay, let me draw it here. So the plant transfer function is going to be 4 divided by S times S plus 2, right? So this is U of S and we get a Y of S out of it, right? So what do we want to do? We want to design a unity negative feedback system. So this is R of S, the reference input. So we have negative feedback, the feedback path transfer function H of S is 1, and then now we need to design a lead compensator here, right? So what is the transfer function of a lead compensator? It is going to be Kc alpha times Ts plus 1 divided by alpha Ts plus 1, right? So that is the transfer function of a lead compensator. So the task for us is to find the values of Kc alpha and T that would stabilize the closed loop system while meeting the above performance requirements, right. So, that is the problem statement, that is the task before us, right. So, that is what we need to do when we solve this problem, right. So, let us go step by step. Okay. So, what we are going to do is the following. So, let us do it step by step. So, please note that G of s, which is going to be equal to C of s times P of s. So, please remember, this is our controller transfer function, this is our plant transfer function, right. So, I am using the same what to say notation as we have been doing throughout the course, right. So, the controller transfer function is going to be Kc alpha times Ts plus 1 divided by alpha Ts plus 1. I am just rewriting in this form, I am just putting Kc alpha here, and the plant transfer function is going to be 4 divided by S times S plus 2, right. So, that is what we have. So, this is C of s and this is P of s, right. Let us call this Kc alpha is defined as some k, okay. That is, the parameter k is defined as Kc times alpha, okay. So, this would essentially tell me that the forward path transfer function, that is G of s, which is the product of the controller transfer function and the path plant transfer function, is going to be Ts plus 1 divided by alpha Ts plus 1 times P1 of s, okay, where the transfer function P1 of s is going to be equal to k times P of s, okay. So, that is what we have. So, what are we taking as P1 of s? This particular block, okay. So, this is my this is what we call as P1 of s, right. So, I am just rearranging the terms, that is pretty straightforward, okay. So, of course, here please note that like here k is essentially Kc alpha, right. So, that is something which we already know, okay. So, having rewritten in this form, let us proceed and see what we do, okay. So, the first step is to adjust k, right, such that the desired value of KVE is obtained. Okay, so that is the first step. So, in the first step what we do, we adjust this k, this parameter k, so that we what to say get the desired value of KV, which was essentially specified as 20, right. So, recall that what was KVE? If you recall our discussion on steady state error characteristics, KVE we defined when we were dealing with like errors to a unit's ramp reference input. Do you recall? Okay. So, that was essentially defined as limit s tending to 0 s times g of s times h of s, right. So, here h of s is 1 in this particular problem. Okay, please note that we are considering unity feedback, right. So, h of s is 1 in this problem, right. So, this is the definition of KVE. So, what will we have? We will have this to be limit s tending to 0 s times g of s is going to be this. So, we are going to get Ts plus 1 divided by alpha Ts plus 1 times k times 4 divided by s times s plus 2. Okay, so, that is what we have. So, now what is going to happen? What are we going to get if we substitute the limit s tending to 0? take the limit s tending to 0, we are going to get 2k, right. That is what we are going to be left with. Please note that this s and s will cancel, and then like we are going to be left with 2k. Okay. So, since KVE should be 10 per second, so we immediately get that 2k should be equal to sorry not 10, right, 20, right. So, 2k should be equal to 20, that implies that k should be equal to 10, right. That is what we have. So, the value of k should be 10. So, this implies that kc alpha is nothing but 10. Okay. So, this is what we get. Okay. So, you see that we are using the required value or the performance specification on KVE to get the value of k, right. Okay. So, once we do this, let's rewrite the the forward path transfer function and P1 of s. So, thus we can immediately see that P1 of s, which is k times P of s, that is going to be equal to 10 times 4 divided by s times s plus 2, that is going to be equal to 40 divided by s times s plus 2. Okay, it will become clear why I am doing this. Okay. So, let's look at this way. So, this implies that g of s is going to be equal to t of s plus 1 divided by alpha t s plus 1. Okay, this is going to be one block. Okay. So, times 40 divided by s times s plus 2. This is the second block. Okay. So, I hope everyone agrees. Okay. So, I hope things are clear till this point, right. So, what have we done? We have essentially considered the structure of a lead compensator. We have just integrated that with the plant transfer function which has been given to us, and calculating the open loop transfer function and equating it to the desired value of KVE. We have found the value of the parameter k, which is kc alpha, and okay. So, we have rewritten the essentially open loop transfer function in this way. Please note that this is the open loop transfer function, right. Why? Because h of s is 1. Now, what is the next specification we have been given? So, what we have done is that we have now essentially used this specification, right. KVE equals 20 per second, right. Now, we are given that the phase margin should be at least 50 degrees. How did we calculate the phase margin for this class of negative feedback systems? We have to essentially calculate 180 degrees plus the phase of the open loop transfer function and the gain crossover frequency, right. So, that is the equation for calculating the phase margin, right, if you recall. Okay. So, the phase margin should be at least 50 degrees. So, you immediately see that the phase margin gamma is going to be 180 degrees plus the phase of the open loop transfer function at the gain crossover frequency, right. This is the general formula, right. In this case h of s is 1, so I am just considering only g of s. Now, you see that the phase of the open loop transfer function comes from two components. What is the first component? It is this Ts plus 1 divided by alpha Ts plus 1. Okay. The second component is this. Okay. So, we have already seen as in the previous class that the lead compensator provides a positive phase, right, is it not? So, the factor Ts plus 1 divided by alpha Ts plus 1 would provide a positive phase to the open loop transfer function. Okay. So, thus it will essentially increase the phase margin, right, but the question is that by how much should I increase the phase margin, right. For that I should figure out what is the contribution of 40 divided by S times S plus 2 the phase margin. See what is the, suppose if I do not have what to say any compensation, what is the phase margin of the uncompensated system, right? How do I find that? I essentially find what is the phase margin which I will get if I just consider 40 divided by S times S plus 2. Okay, so that is what we are going to do now. So if I calculate what will be the phase margin which I will get with just 40 divided by S times S plus 2, I can know how much additional positive phase I need to provide by using the first factor Ts plus 1 divided by alpha Ts plus 1, because we know that when we have product of two transfer functions, right, the net phase is going to be the sum of the two individual blocks. Okay, so we already know that. Okay, so that is what we are going to do. So the second step is to essentially do this and find alpha. Okay, so the second step is to find alpha. Okay, so for that let us first consider P1 of j omega, okay, which is 40 divided by j omega times j omega plus 2, right. Find its phase margin. Okay, so that is what we are going to get. So why are we doing this? Because you see that immediately this phase margin is going to be, if I split this into two factors, this is going to be the phase margin of this factor 1 plus phase margin, phase of factor 2, right. Let us first figure out what is 180 plus 2, then we will know what should be 1, so that I achieve at least gamma of 50 degrees, that is the idea here, right. So let us find its phase margin. So how do I find the phase margin of this factor? What should I first do? I have to find the gain crossover frequency for this factor, right. So how will I find the gain crossover frequency of this particular factor? First, find its gain crossover frequency omega g. So what is the definition of gain crossover frequency? It is a frequency at which the magnitude of this particular sinusoidal transfer function becomes 1, right. So that is the definition. So this implies that by definition 40 times the magnitude of j omega g plus 2 should be 1, or in other words what we should get is 40 divided by omega g times square root of omega g squared plus 4 should be equal to 1, right. We have already done this exercise. So if you do this, you will get omega g power 4 plus 4 omega g squared minus 1600 is going to be equal to 0, right. So this is something which we already know. So if you simplify this, you will get omega g to be equal to, if you do the calculations and simplify this, you will get omega g to be around 6.17 radians per second. Okay, so that is what you will get. Okay, so this will imply that the phase of P1 j omega g is going to be equal to minus 90 degrees minus tan inverse of omega g by 2, right. So that is something which we already know, right, because 40 is not going, it will provide a phase of 0, 1 by j omega will provide phase of minus 90, 1 by j omega plus 2 will provide a phase of minus tan inverse of omega g by 2, right. So this is something which we already know, right. If you calculate this, you will get the phase of this factor P1 j omega at the gain crossover frequency to be minus 162.04. So this implies that the available phase margin for P1 j omega, okay, which is the uncompensated system. Suppose if I do not multiply the second factor Ts plus 1 divided by alpha Ts plus 1. So, what this means is that without, right, Ts plus 1 divided by alpha Ts plus 1, okay. So, that is going to be equal to 180 degrees, right, plus P1, the phase of P1 and j omega g, that is going to be 180 degrees minus 162.04, okay. That is going to be, how much is that? That is 17.96 degrees. So, that is close to around 18 degrees, right. How much phase margin do we want? What is the performance specification? At least 50. So, are we meeting the phase margin specification? No. So, you immediately see that the uncompensated system does not meet the phase margin specification, okay. Okay, so that is what is happening. So, this implies that the uncompensated system does not meet the phase margin, the phase margin specification. Okay. Does the uncompensated system satisfy the gain margin specification? Of course, we'll continue with this, but before we carry on, see what was the third requirement? The gain margin should be at least what was that? Should be at least 10 decibels, right? So, that was the third performance specification. Does the uncompensated system meet the gain margin specification? So, what do I mean by uncompensated system? Once again, P1 of j omega. You will immediately see that the phase crossover frequency for this is infinity. So, the gain margin is once again going to be infinity decibels, right. So, it does meet the gain margin specification, but it does not meet the phase margin specification. Okay, I am not repeating it because we have already done this as an example, right, in the previous class, because you see that here this is a second order system, right, which does not have any pole or 0 in the right of plane. So, immediately see that the phase crossover frequency is going to be infinity, right, because what is phase crossover frequency? The frequency at which the phase becomes minus 180. When will the phase become minus 180? This is the phase, right. You forget omega g. In general, the phase of P1 j omega is going to be minus 90 minus tan inverse of omega by 2. So, this implies that the phase crossover frequency is infinity, right, because that is going to become minus 180 only at infinity. So, this implies that the gain margin of the uncompensated system is going to be infinity decibels, right. So, that is what it is, right, because when you go to infinite frequencies, that is higher frequencies, the value of the magnitude plot, log magnitude curve of P1 j omega is going to go towards negative and negative value, right. It is going to tend to minus infinity. Why? Because the slope of the curve will go as minus 40 decibels per decade. You can immediately see that n is 2, m is 0, right, for this particular plant transfer function, right. So, the slope of the log magnitude curve will go like minus 20 times n minus m decibels per decade. That is something which we already seen. So, the slope of the log magnitude curve will go as minus 40 decibels per decade. So, that means that essentially the value of the magnitude of P1 j omega goes to minus infinity decibels as omega tends to infinity, and gain margin in decibels is the negative of that. So, gain margin tends to plus infinity, right. So, you see that the uncompensated system does satisfy the gain margin requirement, right. So essentially this is an aside. So the uncompensated system has infinite gain margin, okay. So but then the phase margin is not sufficient, right. So that's why we need to do some design here, right. So let me put it this way, okay. So within a box, okay. So essentially we do not meet the phase margin specification. So now what should be the minimum phase that the factor Ts plus 1 divided by alpha Ts plus 1 should add as a lead compensator to ensure that the phase margin goes to at least 50 degrees? See, the factor 2 P1 of S has gives a phase margin total, that is 180 plus 2, okay, is what, 18 degrees, around 18 degrees. So what should be 1 so that phase margin is at least 50? 50 minus 18, right, what is that? 32, right, around 32 degrees is what should be the phase contribution of the factor Ts plus 1 divided by alpha Ts plus 1. But there is a catch here, right. What is the catch here, right? Let's go back and look at the Bode diagram that we constructed yesterday. See, yesterday, you know, like if you forget this factor 0.1, right, and just consider Ts plus 1 divided by alpha Ts plus 1, what do you observe? You see that the magnitude curve is going to start at 0 decibels and then like it's going to increase and then it's going to settle down at 20 decibels, right, at steady state, right. So as omega tends to infinity, and we are going to get the maximum phase at the geometric mean of the two corner frequencies. This is something which we have already seen. Now what's going to happen at this geometric mean? You immediately see that this factor Ts plus 1 and alpha divided by alpha Ts plus 1 would have already added some magnitude, some positive decibels, right, because the magnitude of Ts plus 1 divided by alpha Ts plus 1 will not be 0, right, it will be some small positive, finite positive number. So what's going to happen is that the open loop transfer function, which is now the product of factors 1 and 2, will essentially be influenced by this magnitude of 1 which will come in, and consequently the gain crossover frequency would be slightly shifted to the right. The gain crossover frequency would increase. What is the definition of gain crossover frequency? It is a frequency at which the magnitude becomes 1 or 0 decibels, right. For the uncompensated system, the gain crossover frequency was 6.17 radians per second, okay. Now with compensation, you immediately see that the magnitude of g of j omega is going to be the magnitude of factor 1 plus magnitude of factor 2, what I call as 1 and 2 here, right. Now you see that the magnitude of factor 2 has a gain crossover frequency of 6.17 radians per second, but at that frequency the magnitude of 1 is not 0, right, because it's going to be some slight positive decibels, right, because that's the frequency at which I want to add some phase, right. So you immediately see that with compensation the value of the gain crossover frequency would increase. And if this value of gain crossover frequency increases, you immediately see that the phase of this factor 2 will become more negative at the increased gain crossover frequency. So although we may want to provide a 50 degree phase margin, the effective phase margin would be lower because of the shift in gain crossover frequency, okay. So let me repeat these points once again, okay. Let's go through these points once again. So what have we done? So the open loop transfer function is this, right? So everyone is convinced about that, right? So now there are two factors, 1 and 2, right? 2 is what we call as the transfer function of the uncompensated system, because it's not going to affect the phase margin as such, right? So you see that for the uncompensated system, we calculated a gain crossover frequency and a corresponding gain margin, right? Okay. So now we are considering the compensated system. In the compensated system, this factor 1 comes into play, right? Ts plus 1 divided by alpha Ts plus 1. Now, previously we considered only 40 divided by S times S plus 2. For that factor, the gain crossover frequency was 6.17 radians per second. With this additional factor, which will contribute as positive magnitude in decibels, that means that the gain crossover frequency of the compensated system would increase. I am sure all of us agree, right? Because the gain crossover frequency is going to be the frequency at which the magnitude of the open loop transfer function is 1, right? So now you see that the magnitude of g of j omega is going to be magnitude of 1 times magnitude of 2, or magnitude of 1 in decibels plus magnitude of 2 in decibels, right? Previously we equated the magnitude of 2 to 1 and then got 6.17 radians per second as the gain crossover frequency. But now I am essentially introducing a new factor 1 whose magnitude is going to be greater than 1, okay, at this frequency. So now what's going to happen? Consequently, this would imply that the gain crossover frequency of the new system would increase, right? Isn't it? Because I am multiplying the magnitude of 2 with a number which is greater than 1, right? So at 6.17 radians per second, the magnitude of 2 is 1, but the magnitude of 1 will be greater than 1. So consequently, it will no longer be the gain crossover frequency of the compensated system, right? For which the open loop transfer function is the product of 1 and 2, right? So, but if the gain crossover frequency increases, what will happen? Note that the phase of 2 becomes more negative as omega increases, right? So, the phase contribution of factor 2, right? Now, with the new gain crossover frequencies is more, the factor 2 will be more negative. So, if I just keep the phase contribution of the lead compensator to be 32 degrees, I am going to be still not be in a position to meet the phase margin, because it will be less than 50, because what has happened? The gain crossover frequency has shifted to the right. So, consequently, the phase contribution of factor 2 has become more negative. So, the gain margin would reduce. So, what we do is that as a rule of thumb, we essentially say that the uncompensated system does not meet the phase margin specification, and at first glance the lead compensator should provide a phase of 50 degrees minus 17.96 degrees, right, which is going to be what, 32.04 degrees. That is what we can observe at first glance, right.